Today's topic is normal distribution. Under normal distribution, we are going to look at two different stuff. The properties of normal distribution and the uses of normal distribution. First, let's look at the properties of normal distribution. So if I plot a normal distribution on x and y axis, the curve comes out to look something like this. So this is what the curve representing normal distribution looks like. From the curve itself, you can already determine few properties of normal distribution. The first property being, since normal distribution when plotted on a graph looks like a bell, so it is bell shaped. So normal distribution is bell shaped. Second, when you draw a perpendicular line from the middle of the graph, it will divide the graph into two equal halves. So this is one half and this is the second half, and both of these halves are equal. So we can also say that normal distribution is bilaterally symmetrical. Let me explain you this even better. So let's say this graph on x-axis contains height of people in ascending order. On y-axis contains the frequency or the number of people. So we have a sample of people and we observe the height of individual people. On x-axis we arrange these heights in ascending order. On y-axis we keep the number of people. So when we observe the heights of various people, we see that there are few people there that are quite short. So there are few people that are quite short. And then there are also few people that are quite tall. So you have people that are quite tall. But most of the people lie in this particular area. That is around your central height. So perpendicular line is drawn such that it touches the central height. So there are few people that lie at two extreme position, but then majority of the people, they lie around the central position. That is, the frequency is small at two extremities, the frequency is high around the central position. So there are few people that have height less than central height, and then there are people that have height more than central height. The number of people that have height less than central height is equal to the number of people that have height more than normal height. More than central height. That is how the graph is bilaterally symmetrical or divided into two equal halves when a perpendicular line is drawn through it. Okay. Now, property number 3. So I talked about this central height, right? Or basically in mathematical term, the central tendency, right? The question is, what exactly is this central tendency? Is it mean? Is it median? Or is it mode? And the answer is mean, median, and mode. That means at that particular point, the mean, median, and mode, they coincide. So this point does not just represent mean, it also represents median and mode. Let's say the central height upon observation comes out to be 5 feet 6 inch. This means that 5 feet 6 inch is the mean for the given distribution, is also the median for the given distribution, and it's also the mode for the given distribution. So the final conclusion, mean is equals to median is equals to mode. Property number 4. Normal distribution is seen for various types of variables that are present in nature. So ND, for example, for height, for weight, for blood pressure, etc. Then for normal distribution, there are two different aspects that you need to know. First is the central tendency, and the second is the standard deviation. As I said, central tendency or mean, median, and mode for normal distribution is present at the same point. And this central tendency, now this is the fifth property that you need to know. The fifth property. The central tendency, let's say I'll take the mean. The mean of normal distribution characterizes its position. Let me show you with the help of a graph. So let's say I have a graph for normal distribution right here. For this particular normal distribution, the mean value is present right here. So this is the mean. So obviously the graph is going to be on either side of the mean value symmetrically present. So the graph is symmetrical present on the left hand side, and it is also symmetrically present on the right hand side. But then let's say I move this mean slightly to the right. So I move this mean slightly to the right. So the new mean is present right here. Again, the graph needs to be bilaterally symmetrical about the mean with the same frequency. So the graph is going to move to the right as well. So as the mean shifts to the right, the graph shifts to the right as well. If I shift the mean to the left, then the graph is going to shift to the left as well. This is what I mean by the mean of normal distribution characterizes its position. Property number 6. Standard deviation characterizes the spread of normal deviation. Let's look at two different graphs. Graph number 1 and graph number 2. Graph number 1 is quite tall. Graph number 2 is widespread. Graph number 1, on x-axis, I have height of newborn, and on y-axis, we have number of newborn, or basically the frequency. In graph number 2, on x-axis, I have height of adults. In y-axis, I have number of adults. Let's say the area under the graph for both is same. Okay. Now this is what I want to say. In the first graph, you can see that the graph is taller, while the second graph is flatter. What is the reason behind it? In the first graph, the mean value is 20 inch. That is, the mean of newborn is 20 inches, while the mean of heights of adult is 70 inches. The average height of newborn is 20 inches, and the average height of adults is 70 inches. In first graph, there's less probability of having wider range of heights. That is, the height of a newborn is usually in between 19 inches and 21 inches, and mostly it's 20 inches. So there is less probability of having various heights around the mean height. While in second case, there's higher probability of having wider range of heights around the mean height. So around this mean height, there's possibility of having a wider range of height. That is, the height of the adult can be 71 inch, 72 inch, 80 inch. There is a higher probability of the heights of adult. There are various types of adult that are present in society. Some adults have height of 70 inch, some adults have height of 71 inch, some adults have height of 69 inch. But then, in case of newborn, the possibilities of heights are quite limited. That is, in a newborn, mostly the heights fall between 19 inches and 21 inches. This basically means that there is less dispersion or small standard deviation in heights of newborn, and in second case there is higher dispersion or there is large standard deviation in case of heights of adults. Since there is small standard deviation, the graph comes out to be less spread but more tall. Since there is larger standard deviation, the graph comes out to be more spread and less tall. See, since the area under the graph is same, in order to compromise for the given length or height, the width decreases. Since the area under the graph is same but the width has increased, the tallness decreases. Property number 7. The normal deviation is unimodal. How? So this is what a normal deviation looks like. There is only one single peak value. So there is a single peak value. Since there is a single peak value, there is a single variable for which there is the highest frequency. Because on x-axis you have the variable and on y-axis you have the frequency. So there is a single variable for which the frequency is highest. Property number 8. So this is the curve for standard deviation. And if you look at this curve closely, you can see that on top it is convex. So the distribution is convex from top, but then it is concave on side. The distribution is concave on side. There is a particular point on the graph, and at this particular point the convexity of the graph changes to concavity of the graph. So for this particular graph, it is exactly at this particular point when the convexity changes to concavity. So before that the graph is convex, and after that the graph becomes concave, and this particular point we call it the point of inflection. So what is point of inflection? Point of inflection is the point on normal distribution at which the convexity of the graph changes to concavity of the graph. Right at the middle you have your central value, or let's say the mean. So here's the mean. If you draw perpendicular lines from point of inflection, both in front and behind the mean, a deviation comes out from the mean, and this deviation is equal to +1 standard deviation on the right and -1 standard deviation on the left. And the total area within the standard deviations come out to be 68%. If you don't understand these stuff, let me make it more clear with the help of a rule that is applicable for normal deviation. And this rule is called your 68, 95, 99 rule. Let me show you what this means. Let me draw a huge graph. Okay, so this more or less looks like a normal deviation. Okay, in this particular normal deviation, at the midpoint you have your mean. So here's the mean. If you go one standard deviation in front and behind the mean, one standard deviation. So one standard deviation to the left and one standard deviation to the right. So mean plus minus one standard deviation. The area incorporated within that much of the graph. So the area incorporated within mean plus minus one standard deviation of the graph is equal to 68%. So you can also say that the total values incorporated in that much part of the graph is 68% of the total values. Similarly, if you increase standard deviation to 2 standard deviation to the right and to the left of the graph from the mean. So you have mean plus minus 2 standard deviation. That much of the graph is going to incorporate 95% of the total values. It's going to incorporate 95% of the total values. Again, let's increase it by one more standard deviation. So mean plus minus 3 standard deviation. 3 standard deviation to the left and 3 standard deviation to the right. That much of the graph, this much of the graph is going to incorporate 99% of all the values. 99% of all the values. So let me complete the diagram by drawing perpendicular lines from each of the standard deviations. Okay. So what is this? This is mean plus 1 standard deviation, mean minus 1 standard deviation. Again. What is this? This is mean plus 2 standard deviation. This is mean minus 2 standard deviation. What is this? This is mean plus 3 standard deviation and this is mean minus 3 standard deviation. Again, the area within the graph that inculcates mean plus minus 1 standard deviation is equal to 68% of the total area or the 68% of total values. The area within the graph that incorporates mean plus minus 2 standard deviation is equivalent to 95% of the total area or 95% of all the values. Again, the area within the graph that incorporates mean plus minus 3 standard deviation is equivalent to 99% of the total area of the graph or 99% of all the values. So this is your 68, 95, 99 rule. Okay, there is last property that's still remaining. Number 10. Normal deviation is only valid when you have a large or infinite sample size. So you might have already seen in the graph, this particular part is almost never ending. It goes on forever. That's because the sample size is infinitely large. But then let's say you take a limited sample size. In that case, instead of getting a normal deviation, you end up getting something called skewed distribution. Instead of getting normal distribution, you get skewed distribution. In skewed distribution, the graph is tilted on one side. That is, it looks something like this. So we have a limited number of people. In that case, the graph ends up looking like this. So it's not bilaterally symmetrical. Instead, it is tilted on one side. So these are the properties of normal deviation. One last revision for all the properties. First property, since the graph looks like a bell, it is bell-shaped. It is bilaterally symmetrical. When you draw a perpendicular line, it divides the graph into two equal halves. Normal distribution is seen in case of variables like height, weight, blood pressure, etc. When you shift the mean on either side, the graph gets shifted on either side as well. The standard deviation, it determines the spread of normal distribution. If standard deviation is less, the spread is less. If standard deviation is high, the spread is more. There is only one single peak value, so there is only one single mode, so the distribution is unimodal. The graph is convex from the top, and as you go down it becomes concave, and the point at which the convexity changes to concavity is called point of inflection. There's your 68, 95, 99 rule, which says that mean plus minus 1 standard deviation inculcates 68% of the values, mean plus minus 2 standard deviation inculcates 95% of the values, and mean plus minus 3 standard deviation inculcates 99% of the values. For you to get a normal deviation, the sample size needs to be large or infinite. We have a normal distribution right here, the mean of which is represented by mu. On either side of the mean, you have values that deviated either in front of the mean or to the back of the mean. If you move one standard deviation in front of the mean, you get the value mean plus 1 standard deviation. Similarly, 2 standard deviation in front, mu plus 2 standard deviation. And similarly, 3 standard deviation in front, mu plus 3 standard deviation. And in normal distribution, it is usually till 3 standard deviation in front or back of the central value that the graph incorporates all the values. So when you go back as well, it will include mu minus 1 standard deviation, mu minus 2 standard deviation, and mu minus 3 standard deviation. So the graph incorporates values in between minus 3 to plus 3 standard deviation away from the central mean value. So this is what usually the graph incorporates. But that's not the main thing here. The main thing is that this right here is your normal distribution. And normal distribution is applicable for various kinds of variables that are present in nature, like your height, weight, blood pressure. And height, weight, blood pressure, they have their own units like kg, meter, inches, feet, inches, and then millimeter of mercury. And then they have their own values. Let's say you go to a town and observe the heights of the people there, and the mean height comes out to be 73.5 inches. 73.5 inches, and the standard deviation comes out to be 2.5 inches. Then one standard deviation in front is going to be 73.5 plus 2.5. 2 standard deviation in front is going to be 73.5 plus 2.5 plus 2.5. So it's quite messy to deal with when you use this particular graph right here, which is completely unstandardized. In order to make the graph simple, what we do is we simply standardize the graph. We standardize the graph. How do we do that? We do that by representing the mean value with the value 0. So we put the mean as 0. And when you go one standard deviation in front of the mean, you are going to get plus 1. 2 standard deviation in front of the mean, plus 2. 3 standard deviation in front of the mean, plus 3. So this is what it is going to look like. Plus 1, plus 2, plus 3. To the back, minus 1, minus 2, minus 3. The question is, how exactly do you standardize a normal deviation? You standardize normal deviation with the help of something called z-score. So z-score helps you standardize a normal deviation. Mathematically, z-score is equals to x minus mu by sigma. So here's one formula that you need to know. Z equals to x minus mu by sigma, where z simply means the z-score, x means the value of the variable, mu means the mean, and sigma means your standard deviation. Let me give you an example. Let's say you went to a class where the mean weight comes out to be 70 kg and the standard deviation of the weight comes out to be 2 kg. So if you were to represent it in an unstandardized normal deviation, you'd keep the mean value as 70 kg, and then on either side, on moving one standard deviation away, you'd get 70 plus 2, 72 kg, 70 minus 2, 68 kg. And the graph would complete with values something like this: 74, 76, 66, 64. Now, in order to make this normal distribution standardized, you need to do the following thing. First, you are going to put the mean value as 0, 0, and represent the rest of the values with simply how many steps in front or back do you go. So this is going to be +1, +2, +3, -1, -2, -3. Let's say the weight of a certain student named A is equals to 73 kg. Then the Z score comes out to be X, which is 73 kg, minus mu, which is 70 kg, divided by 2, which is the standard deviation. So 3 by 2 or 1.5. What exactly does this 1.5 mean? 1.5 is the Z score, and this tells you how many standard deviation is the value away from mean. So in this case, how many standard deviation is the weight of student A away from the mean weight? So it is 1.5 standard deviation away. So it is present right here at this point. This is where the student that you selected is present.